Hey everyone, today I want to talk about a little energy physics problem, and the setup for this is very simple. You're simply throwing a ball into the air. In situation A, you happen to be throwing it in a vacuum, so the only force acting on the ball is gravity. In situation B, you're throwing it up not in a vacuum, right? So you're going to have gravity pushing down on the ball, and you're also going to have some air resistance, which I've labeled here F, pushing against the ball. So the goal of the problem is to determine the maximum height of the ball if A, there is no air resistance, and B, there is some air resistance, which does some work, F times h on the ball. So we're going to go ahead and start by tackling the simple problem A. We can go ahead and use the conservation of energy, so EI equals EF. Recognize that we are able to use this because we're simply looking at the force due to gravity, which is a conservative force. Alright, so from here we can break this down into the following. UI plus KI equals U final plus K final. And now, let's go ahead and substitute some terms in for this. To do this, let's go ahead and just really quickly make a little picture. And the ball is going to go up, and it's going to make some maximum height before going back down. So, I'm going to set the ball at the beginning. I'm going to set this to its initial potential energy, which is equal to 0. If the ball goes up some height h, right, I'm going to go ahead and set this potential energy here to mgh. Alright, so this is going to be U final. Bam. So this is going to end up being 0. This is going to be mgh. What's our initial kinetic energy? Well, it's simply based on what our initial velocity that we throw the ball with is. So that is going to be 1/2 m times v naught squared. Our final kinetic energy, because it's going up, slowing down, it stops momentarily at the top, so it has 0 kinetic energy before falling, right? So, our ball has 0 kinetic energy at the end of its trajectory. Perfect. We recognize that our m's cancel, and so we're left with 1/2 v naught squared equals gh. We solve for h to get h equals v naught squared over 2g. Alright, there's situation A. Situation B, we're going to do almost the same thing, but this time we have a non-conservative air resistance term. And we noted that resistance term is going to do the work F times h on the ball. So I'm going to note that we have EI minus this frictional work that I'm going to label WF, and this is going to equal E final, right? We're losing some energy from the ball due to this resistance. So from here, let's do the exact same thing. I'm going to break up my initial energy into UI plus KI minus WF equals UF plus KF. Alright, now we start plugging in terms, and it's just like before, right? Our UI is going to be 0, our U final is going to be MGH, our K final is going to be 0, our KI is going to be 1/2 M times V naught squared, and our work lost by that friction is F times H. So we substitute for this H times F, right? Let's go ahead and write this out in a nice clean line. From here, I'm going to move my HF term to the other side of the equation, and I'll just go ahead and rotate it like this. Let's go ahead and take out our H, because that is what we want to isolate. And from here, I'm going to isolate my H term. So we get MV naught squared over 2 times F plus mg. And perfect. So we were able to tackle this problem with the conservation of energy in part A, and in part B we just slightly modified the conservation of energy to take into account our resistance term F, which was a non-conservative force. So I hope you enjoyed that little video, and thanks for watching.